Welcome to my tutoring session in chemistry. The current video is part 4 of the 5-part series in thin layer chromatography. In this video, I'll explain the intermolecular forces involved in the thin layer chromatographic separation technique. This will be followed by a detailed explanation about the development techniques employed in TLC. And finally, I'll end the video with the methods employed for the preparation and activation of the TLC plates. Now, chromatography is a separation technique which is commonly employed for the separation of the given sample mixture into individual components. Now, the TLC plate is prepared by applying the silica gel slurry over the glass plate, whereby we get a thin layer of silica gel over the glass plate. Dry the plate, activate the plate. Now, draw a baseline at the lower end of the TLC plate. Mark a reference spot on the baseline where you are supposed to apply the sample. And finally, you can apply the sample over the baseline using microsyringe, micropipette, or even a capillary can also be employed. So now the plate is ready for development. Introduce the plate into the TLC chamber and make sure that when you introduce the TLC plate into the chamber containing the solvent system or the mobile phase, the level of the solvent should be below the baseline over which the sample is applied. Now here we see that in this particular diagram, the level of the mobile phase is above the baseline over which the sample is applied. So when this happens, the sample will be washed away as the sample is submerged in the mobile phase. So this is not the correct way of doing it. Now the right way of doing it is when you introduce the TLC plate into the chamber containing the mobile phase, make sure that the baseline over which the sample is applied is slightly above the mobile phase. Now during development, the solvent system which acts as a mobile phase, it travels or moves through the stationary phase by capillary action. Now the sample that is sandwiched between the stationary and the mobile phase, it travels over varying distance on the stationary phase. Now the distance traveled by the compound being separated over the stationary phase depends on its relative affinity towards the stationary phase as well as towards the mobile phase. Now the principle that the TLC works on is adsorption. So principle of separation in case of TLC is adsorption of the compound over the stationary phase during the separation process. Now the principle is one and the same both in case of TLC as well as in case of column chromatography. Only differences in case of TLC, a thin layer of silica gel slurry is applied over the glass plate, while in case of column chromatography, the silica gel slurry that is prepared, it is filled into the glass column. In TLC, the glass plate acts as a solid support for the silica gel, while in case of column chromatography, the glass column acts as a solid support for the silica gel slurry, which acts as a stationary phase. Now let's carry out the separation of three components of varying polarity using a non-polar mobile phase, which is a mixed solvent comprising of hexane and ethyl acetate, and a stationary phase, which is silica gel. Now silica gel is a polar stationary phase because of the presence of polar silicon groups, which is characterized by the polar hydroxy groups covalently bonded to the silicon. Now the mobile phase, it moves or travels through the stationary phase by capillary action. So in this particular experimentation, we'll be carrying out separation of three chemicals or three compounds of varying polarity. A polar molecule like paracetamol, a molecule of intermediate polarity like acetophenone, and a completely non-polar molecule like naphthalene. Now paracetamol is a classical painkiller. It is highly polar in nature and it travels over the polar stationary phase covering a shorter distance. This is because of its polar nature and the strong hydrogen bonding interaction with the silicon groups of the silica layer. So it is highly polar in nature and the functional groups, they interact with the polar silicon groups by hydrogen bonding. And because of this intermolecular force, its migration or movement over the stationary phase is hindered and therefore it travels a shorter distance. And it also interacts with the non-polar mobile phase containing hexane and ethyl acetate and it interacts by van der Waals attraction. So the non-polar groups of paracetamol molecule like the benzene ring and the methyl group, they interact with the non-polar mobile phase via van der Waals attraction. Now detailed explanation about hydrogen bonding and van der Waals attraction is given in my previous videos. Now the description, the link to this videos is given in the description below. So please do watch those videos. And these videos will provide you with a better understanding of this video content. Now this is followed by a molecule of intermediate polarity like acetophenone. It travels further distance as compared to the highly polar paracetamol molecule. Now acetophenone is of intermediate polarity because it is having only one functional group with electronegative oxygen atom, which is indulging in hydrogen bonding with the silicon groups of silica gel layer. So the number of hydrogen bonds which the acetophenone molecule indulges with the polar silicon groups of the stationary phase is much less as compared to that of paracetamol molecule. So the relative affinity of acetophenone towards the stationary phase is much less as compared to that of polar paracetamol molecule, and therefore it travels distance further as compared to that of polar paracetamol molecule. Now what about its interaction with the mobile phase? So it interacts strongly with the non-polar mobile phase constituted by non-polar hexane and ethyl acetate molecule. So that is also one of the reason why it is dragged for a longer distance. Now what about the non-polar naphthalene molecule? Now the non-polar naphthalene molecule, it travels a longer distance as compared to that of the acetophenone and polar paracetamol molecule. This because, as you can see, the non-polar naphthalene molecule, it has no functionalities to interact or indulge with the polar silicon groups. So there is no interaction between the non-polar naphthalene molecule and the polar silicon groups. But there is strong van der Waals attraction or interaction between the non-polar naphthalene molecule and the non-polar mobile phase. And therefore, the major force that is dragging the non-polar naphthalene molecule over the length of the stationary phase is van der Waals attraction. So it is van der Waals attraction which is dictating or governing the motion or movement of the nonpolar molecule. Now the principle of separation in case of TLC is adsorption, where the sample molecule is getting distributed between the mobile phase and the stationary phase. Now stationary phase is polar silica gel, mobile phase is a mixed combination, a mixed solvent. We have used hexene and ethyl acetate. So three components A, B and C, and these three components are being separated individually using a polar stationary phase. Now the reference line at the upper end of the TLC plate refers to the distance traveled by the mobile phase. Now the blue spot refers to the distance traveled by the nonpolar naphthalene molecule. The green spot refers to the distance traveled by acetophenone molecule of intermediate polarity, while the purple spot refers to the distance traveled by the polar paracetamol molecule. Now the samples are initially applied over the baseline. So this is the separation details when the samples are spotted individually. Now let us try and carry out separation of these three components together. We prepare a sample mixture of all three components A, B and C, and this is the resultant TLC profile, where we see the separation of the sample mixture into individual components, and the distance they travel depend on its relative affinity towards the stationary phase. An RF value can be calculated using the formula distance traveled by the compound from the baseline over the distance traveled by the solvent from the baseline. Now the non-polar naphthalene molecule is labeled as A. Acetophenone molecule of intermediate polarity is labeled as B. And paracetamol molecule, which is highly polar in nature, is labeled as C. Now four major intermolecular forces govern or dictate the migration or movement of the components or the molecules over the stationary phase. They are hydrogen bonding, van der Waals forces or van der Waals attraction, dipole-dipole interaction, and rarely you will come across the coordination interaction between the component and the stationary phase. Now let's talk about some of the methods employed for development of the TLC plate. Now the commonly employed method for developing the TLC plate is the one-dimensional chromatographic method, where you draw the baseline over the lower end of the TLC plate, apply the sample, and when you introduce the TLC plate in the chamber, development chamber, the solvent front, that is the mobile phase, it moves or travels over the stationary phase by capillary action, and in the process you can see the sample is getting separated. The second method is the two-dimensional chromatographic method. It's a quite interesting method that can be adopted for separating complex mixtures, where you find the sample mixture is made up of nearly 7 to 10 components. Now you cut the TLC plate into suitable dimension, draw margin lines, true margin lines over two sides of the TLC plate. You will find that the two margin lines that you have drawn at the two sides of the plate, they intersect at a particular point. Apply the given sample mixture over the point where the two margin lines intersect. Now the arrow indicates the direction of development of the mobile phase or the direction in which the mobile phase travels through the stationary phase. So we are developing this TLC plate using the first solvent by ascending technique. And after the separation, we find that the given sample mixture has separated into 3 individual components, highlighted here in red, blue and green spots. Now after the separation is done, dry the plate and turn the plate at right angle by 90 degrees. And now carry out the separation with a second solvent. And remember, the arrow indicates the direction of development. It indicates the direction in which the solvent flows through the stationary phase. Now in the second development, you will find that the component, that is each component, has further separated into 3 different components. So overall you find a total of 9 spots in the TLC plate, and this will be the final separation. So to conclude, the given sample is a multi-component mixture with 9 amino acids. And advantage of this two-dimensional method is that the complex mixtures can be separated into individual components by this 2D method. Now the TLC plate is developed in one direction with first solvent, and later the TLC plate is developed in the second direction. Now the separation of complex mixture is not always possible in one-dimensional chromatographic method, because there is every possibility that spots may overlap. And when the spots overlap, you will be presuming that lesser number of components are present in the given sample mixture. So 2D method can be employed when you are trying to separate complex mixtures. Now let's discuss about the different methods for the preparation of TLC plates. Now 4 methods can be used: pouring method, dipping method, spraying method and spreading method. Of all these 4 methods, spreading method is widely employed, as silica gel layer of uniform thickness can be obtained over the glass plate. And spreaders are commercially available that can be used for spreading the silica gel slurry over the glass plates. Now in case of pouring method, you have to pour the silica gel slurry. Now let's prepare the silica gel slurry. Now silica gel is a solid powder. A suspension or slurry of silica gel can be prepared by mixing the silica gel powder in low boiling solvents like chloroform and stir the resultant suspension using glass rod for a short period of time until you get a even consistency or good consistency of the silica gel slurry. So now the silica gel slurry is ready, and the TLC plate can be prepared by employing these 4 methods. Now in pouring method, now pour the prepared silica gel slurry over the top of the glass plates, and slowly you can see a thin layer of silica gel slurry is being applied over the glass plate. Now the disadvantage with this method is that uniform thickness of silica gel slurry cannot be obtained. Now in case of dipping method, we can make use of microscopic slides available in the laboratory. You take 2 microscopic slides, sandwich both the slides. Now dip the sandwiched microscopic slides into the beaker containing silica gel slurry. And after a moment, you can slowly raise the TLC plates, I mean the glass plates, and you can see a thin layer of silica gel slurry on both sides of the glass plates. Now you can separate both the glass slides and you can prepare 2 slides at a time. Now the disadvantage with this method is that even for preparing 2 slides, we require a large quantity of the silica gel slurry. And in case of spraying method, you take a glass plate of suitable dimension, you fill the sprayer with silica gel suspension and spray the silica gel slurry onto the glass plate. Now again, in case of spraying method, you cannot expect a silica gel layer of uniform thickness. And spreading method is the recommended method where you can get a silica gel slurry of uniform thickness. Now commercially available spreaders can be used. Now how to activate the TLC plates? Now the TLC plates are ready. Now how to activate these TLC plates? Now allow the TLC plates to air dry. So when you air dry the TLC plates, that prevents cracking of the plates. And after air drying and allowing the plates to set, activate the TLC plates by heating in the oven at around 100 degrees Celsius for 1 hour. And why is this activation done? Now activation of the TLC done for 2 purposes. Number 1 is to remove the moisture or water on the silica gel layer and also to remove the any adsorbed material over the silica gel layer. And most importantly, to retain the adsorbent activity of the silica gel. Now the plates so activated, it can be preserved or stored in desiccator or oven, which can be used as and when required. Thank you so much for watching my video. I hope you enjoyed it and I'll meet you in my next interesting tutoring session.